We wrote a treatment for the movie. A treatment is the story, the characters, and the science in the movie. Linda brought onto our project a man named Steven Spielberg to direct the movie. I proposed to Spielberg guidelines for the movie, that nothing in this movie will violate firmly established laws of physics or firmly established knowledge of the universe, and speculations about poorly understood physical laws and the universe will come from real science. Spielberg happily agreed, and then after a long search, in January 2007, Spielberg and Lindoi Obst brought onto our project Jonathan Nolan, Jonah is his nickname, to write the screenplay. I gave Jonah many books about the science in the movie, which he read in detail over about 6 months. Then Jonah and I brainstormed together to develop ideas for the film, and Jonah wrote 3 successive drafts of the screenplay. He changed the first half of the story completely and changed half of the characters in the movie. On June 8, 2010, Spielberg dropped out. He left the project, and so we had no director for a movie that would cost $165 million. There were only about 3 directors in Hollywood with whom Paramount Pictures would trust a movie of this cost, a science fiction movie of this cost. And so it took 2.5 years until Linda was able to bring on a new director for the movie. The new director was Christopher Nolan, or Chris as I call him. And he brought with him a new leading producer, his wife, Emma Thomas. Chris has a strong intuition about the science. He accepted my guidelines to the extent they do not get in the way of making a great movie. And he brainstormed with me about the science through 3 more drafts of the screenplay. He changed the second half of the story completely. And he changed all the characters that his brother had not already changed. But he did not change the science. He kept the science. He preserved our dream, our plan for a movie with science built into the fabric of the film completely from the beginning. So all the science is either mine or joint between me and the Nolans. But beyond that, this Interstellar is their movie and not my movie. In May 2013, Chris introduced me to Paul Franklin, who is the supervisor of visual effects for the movie. Paul had won the Academy Award for the visual effects in Inception. The Academy Award is like the Nobel Prize in movies. And recently, he also, as a result of work with me and his team, he also won the Academy Award for the visual effects in Interstellar. Paul introduced me to Eugenie von Tunzelmann and Oliver James, who are physicists and engineers who speak my language mathematically. I worked with them and with their whole team to make sure that all of the images you see of black holes, wormholes, accretion disks are precisely what you would see in the real universe. I'm going to skip over a film clip which is in English and just move on. Okay. I will show you a later film clip that. So I am a physicist. I am not a filmmaker. My motivation for this was first to have fun and second, for science education. And so I wrote a book about the science of Interstellar, which is being translated into Russian. This book was published simultaneous with the release of the movie worldwide. The only way to completely understand the science in this movie is to read my book. But I will describe some of the science in the remainder of this lecture. Early in the film, there is a discussion by Cooper talking to his daughter, Murph, about the relativity of time. You can read what Cooper says while the translation is being made. You translated? Yeah, okay. In fact, what you see later in the screen, in the movie, is that Cooper lands on a planet called Miller's Planet near a black hole, and he finds that 1 hour on Miller's Planet is 7 years on Earth. This slowing of time is due to gravitational time dilation. That is, it's the effect of the gravity of the black hole and the fact that the planet is so close to the black hole. In fact, when I look at the mathematics of black holes with what is called the Kerr metric for a black hole, I can infer that to get such great time dilation, the black hole Gargantua is the name of the black hole, must spin very fast. Physicists describe this spin by a parameter A, which can never be bigger than 1. In fact, this black hole must have a spin that is less than 1 by just 1 part in 10 to the 14. And the planet must be as close as it can possibly be to the black hole without falling in. So we can describe the planet's orbit quantitatively by what a physicist calls an embedding diagram. If I take a slice through the equator of the black hole, and I look at the geometry of that sheet, it's not flat like the surface of this table. It is curved in a manner that I describe here. It has circumferences that become constant as you go farther and farther and farther. Or we can think of this as our universe embedded in a higher dimensional flat universe, what physicists call the bulk. In the movie, the bulk is called the fifth dimension, and the characters often talk about the fifth dimension. Just once in the movie, Cooper uses the word bulk, once. This is typical of Christopher Nolan, who has many, many ideas in his movies that he hints at by one word or one sentence that is a key to really understanding what is going on in the movie. This was true of Inception, if you saw Inception. It's also true here. Many places where one key word is stated and you never hear it again. If you miss the word, you will not fully understand. As seen from the bulk, this is what a black hole looks like. As seen in our universe, it looks like that. The surface of the black hole, its horizon is down here. Miller's Planet is there. The orbit where the Endurance spacecraft waits for Cooper when he goes to Miller's Planet is up here. In the movie, when Cooper is on Miller's Planet, a water wave 1 kilometer high crashes down on his spacecraft, on his landing craft. This wave is like a tide on the Earth. It is created by the gravitational pull of the black hole Gargantua. Gargantua's gravity deforms the planet like this. The planet keeps the same face always toward Gargantua, but it is rocking back and forth like that, and as it rocks, the water sloshes around on Gargantua's surface like the tides. But the tidal force is so huge that these tides are 1 kilometer high. From the mathematical theory of black holes and tides, we can infer that Gargantua's mass is 100 million times as large as the Sun, and that its radius, or its circumference, the circumference of Gargantua's surface is the same as the circumference of the Earth's orbit around the Sun. So Gargantua is very, very big. It is the same size as the black hole in our neighboring galaxy, Andromeda. The circumference of the black hole is the same as the circumference of the Earth's orbit. Now, in previous science fiction movies, such as The Black Hole made by the Disney studios, black holes are depicted as like funnels. This is from the Disney movie. But this is not how black holes look in our universe. This is wrong. Perhaps they made the mistake of thinking they live in the bulk at Disney Studios and they look in on the black hole. But we do not live in the bulk. And to us, the black hole looks very different. So for the movie, I worked with the team of Paul Franklin to generate images that are precisely the way, almost precisely the way a black hole really looks if you're up close. Now I'm going to ask you not to translate this. This is technical, so designed for the professionals. But the standard method of generating these kinds of images is to propagate light rays or null geodesics from points on an accretion disk around the black hole through the curve space-time to the camera. Let's not translate. I want to move on. Just this one slide, okay? There are 26 million pixels in an IMAX image, and so it required 26 million light rays if we do it this way. We had the problem that when neighboring light rays went close to the black hole, the tidal forces of the black hole pulled them apart. So the grid of light rays was too sparse. And when objects with sharp edges or small stars went across the IMAX screen, by this method, we got flickering. It would go bright, dim, bright, dim. We could not get good images. So we developed a new method of propagating light beams instead of light rays, beams with elliptical cross sections and Gaussian profiles of the intensity distribution. 26 million of these light beams, with the beams overlapping, and then with some smoothing between beams. And this is a new method which we used very successfully. We have documented it in a technical paper, and which physicists can read. And this is already beginning to be used both by astrophysicists for their simulations and in Hollywood for movie making. So our effort gave rise not only to an Academy Award, but also to new techniques for doing visual simulations. So now we can begin translating again, okay? So if I take a disk that is in this form of paint swatches, put it around the black hole, that disk will look to a camera as it looks at that disk around the black hole like this very strange shape. This can be understood quite easily. This is the front of the disk. Well, here is the camera. When it looks at the front of the disk, it sees the disk going in front of the shadow of the black hole. But light rays from the top of the back of the disk go up and over the black hole. They are bent by the black hole's gravitational pull. They come down to the camera, and as a result, the camera sees the top of the back of the disk as though it were above the black hole, which causes this. And light rays from the bottom of the back disk go under the black hole and up to the camera, producing this part of the image. And some of the light rays go off the disk, go around the black hole once and down to the camera, producing this part of the image, and similarly that part from light rays that go around the black hole in the other direction. Now, for our accretion disk, we used a disk very different from those that Igor Novikov and I described in our classic paper following after Shakura and Sunyaev's Newtonian description. Igor and I described relativistic disks. But this disk is very different than ours was. The disk in Interstellar is old, it's cooling down, it's not accreting onto the black hole, there's no magnetic field, no jets. It's emitting black body radiation at 4,500 degrees temperature. This is all for safety of human beings. You do not, as a human being, you do not want to be close to any other kind of disk. So this is what the disk looks like when you use our computer program to compute the image. I'm going to skip over this. So this is what it looks like. I've made a slight adjustment I don't want to discuss. But there are no frequency shifts here, no gravitational redshift, no Doppler shifts. When we put on the frequency shifts, the disk becomes very bright and blue on this side, dark and red on that side, because the gas is moving toward you here and away from you there due to and this is the Doppler shift, the Doppler effect. Christopher Nolan looked at this and said, no. 100 million people will see this movie. And for 90 million of these people, this image will be too confusing. So he said, remove the Doppler shift. This is, if you want to see a complete list of everything he did to the science, this is one of the most serious things. But there's a complete list of all the ways in which, talking with me, we agreed he should change the science a little bit. You look in the back of my book in the subject index, but look for Christopher Nolan, a person, in the subject index. There you will see a complete list of all the ways in which the science was changed in order to make the movie be understandable, or perhaps understandable, to 100 million people. So none of these changes are serious. This is not very serious. And all of them were in consultation with me and by agreement between Christopher and me. Let's return to the black hole Gargantua and its accretion disk. Christopher Nolan was not satisfied yet. He wanted a black hole not as it would be seen by your eyes if you are close to the black hole, but instead as it would be seen through an IMAX camera, because all of the part of the movie that was filmed with IMAX cameras. Similarly, the simulated images must be as seen through an IMAX camera. When the very bright light from this disc goes through the IMAX camera, some of the photons of light get scattered, and the lenses also diffract the light. So for the physicists, Christopher Nolan had the people I work with measure the point spread function of an IMAX camera and convolve that with this image to get the image that you would have that includes scattering and diffraction. So this is the image seen through the IMAX camera. And this is the image you see in the movie and in the advertisements for the movie. Let me next talk about the wormhole in the movie. As seen from the bulk, the wormhole reaches through the bulk from close to Saturn to the vicinity of Gargantua. If you travel through our universe, the distance is 10 billion light years. If you go through the wormhole, the distance is a few hundred meters. There are some severe problems with wormholes, however. The big one is, how do you hold a wormhole open? Because the walls of the wormhole want to pinch off and prevent anything from going through. To hold the wormhole open, you must put into it something with negative energy, which then anti-gravitates, causes the walls to repel to keep the wormhole open. Negative energy does exist in our universe, associated with what are called vacuum fluctuations of quantum theory. But we do not know whether you can have enough negative energy inside a wormhole to keep it open. We don't know. This is controversial. I think probably not. Igor Dmitrievich Novikov here is much more optimistic than I am. Only more research, much more research is needed to find out the answer. For Interstellar, I constructed a wormhole metric, a shape for the wormhole that has 3 parameters that I could adjust: the radius of the wormhole, its length, and how fast the mouth flares out to join onto the universe. Oliver James incorporated this into our computer code. Eugenie von Tunzelmann's team constructed a galaxy near Gargantua with dust clouds, nebulae, and stars. And we propagated the light from that galaxy through the wormhole to the camera in order to produce images. Christopher Nolan looked at the images of the wormhole for various shapes, and he chose the nicest image, and therefore he chose the shape of the wormhole. His chosen image of the wormhole is here. This is what you see in the movie. You are seeing the distant galaxy looking into the wormhole from close to Saturn. This is the shape of the wormhole that gave that image. The next thing to do was to make a movie of traveling through the wormhole. So I will show you such a movie created by the team, by Paul Franklin's team. This is not what you see in, let me say also that we have recently published a paper in American Journal of Physics that presents the methods for computing these images in a form that they can be implemented by advanced undergraduates, physics students. So I'm going to show you a movie of what it looks like to travel through this wormhole. Here is Saturn. It's far away. The wormhole is much closer. This is the wormhole. It looks almost as big as Saturn only because it is much closer to you. Light rays from Saturn that go around this side of the wormhole get bent. They produce that distorted image of Saturn. Light rays that go around the other side produce this very distorted image of Saturn. So I will now show you the movie. We are moving in the spacecraft Endurance toward the wormhole. This is the distant galaxy seen through the wormhole. It seems to push these images apart. You're close to the entrance. You're now entering the wormhole. You're now through the wormhole and you're in the distant galaxy. Nolan looked at this and said, no, this is not exciting enough. He had the team make movies of traveling through wormholes with other shapes. This is the shape of the wormhole that produces the beautiful image from the outside. But he said, for the trip, let's pretend we have a different shape. On April 20th, 2014, when all the filming was finished, they were putting the entire movie together. Chris telephoned me, he said, come to my house, let me show you the problem. So Chris flew to London. Chris and I live in Los Angeles. Chris flew to London overnight and sat down with the team with which I worked. The entire team is in London except me. And they had our artists at this visual effects company, Double Negative, Paul Franklin's artists, combine the images from different trips through the wormhole to produce the final image. For those of you who have seen the movie, this is one image from that piece of the film. But I think it is a remarkable thing about Christopher Nolan that in these very few places where he went away from what the science says, it was done unhappily, but feeling that he was forced to, and in consultation with me. I think there has never been a case of a movie where it was done with such care on the sciences. And I think I should stop here. There's much more I could say, but you can read all of it in my book. I would be happy to answer questions. You decide.
You decide.
15 minutes, maximum. 15. I presume that everything was completely clear and you understood the movie completely, so there are no questions. Is that right? Yeah. So let's, one question at a time. So what is the origin of the bright matter around the black hole? Long ago, this black hole tore a star apart. The same tidal forces as deform Miller's planet for a large star with low density, they will completely tear the star apart. And the gas from the star formed this disk around the black hole. By now, most of that gas has gone into the black hole. Only a small amount is left. And it is sitting there quietly going around the black hole and cooling down as it radiates. Okay, I'll give you one more question and then just one more question from you. Okay, so the question has to do with the end of the film. Christopher Nolan and I talked about the end of the film in our first meeting. Chris said to me, I have always admired Stanley Kubrick and Kubrick's ending of the movie 2001, A Space Odyssey. He said, I want this movie, Interstellar, to have an ending that is as mysterious as the ending of 2001, but an ending that can be explained. And it is true, the ending of Interstellar cannot be understood unless it is explained to you. You can guess, and you can make many interesting guesses about what you are seeing, and you do not have to have an explanation in order to enjoy the movie. It's a tribute to Christopher Nolan that 100 million people went to see a movie whose ending they could not understand. So Chris gave to me the opportunity to explain the ending of the movie, and I explain it in my book. So I will tell you in about 3 sentences, which you will also not understand, but you might understand a little bit. In the end of the movie, Cooper falls into the black hole, not the wormhole. There are 3 singularities inside the black hole. One is more gentle than the other 2. For the experts, it's the shock singularity that was discovered by Amos Ori and Donald Marolf at approximately the same time as I had my first conversation with Chris, just 2 years ago. Cooper gets close to the shock singularity where he falls into a space vehicle called a tesseract, which has been created by a civilization that lives in the bulk, what are called bulk beings. The tesseract lifts him out of our universe into the bulk, or in the language of the movie, carries him into the 5th dimension. In our universe, the distance from Gargantua back to Earth is 10 billion light years, but in the bulk, that distance is only the same as from the Earth to the Sun, quite small by comparison. This is the prediction from a mathematical model for our universe, for the experts, in which our universe is surrounded by a layer of anti-de Sitter space which holds gravity in. The tesseract quickly carries Cooper back through the bulk to Earth, where it docks alongside his daughter's bedroom. And you then see him watching his daughter and sending signals gravitationally to his daughter through the bulk with the help of the tesseract. So that's a brief description of the ending. The most interesting part is his seeing his daughter, sending signals back, and the details of that, which are very exciting, and which I explain the details in my book. Okay, let me answer 2 more questions from 2 other people. Okay, let's take one up here. So in the movie, you see Professor Brand trying to understand gravity. He has 16 blackboards covered with equations. The equations on 1 or 2 blackboards involve Russian characters. I wrote those characters. Yakov Borisovich Zeldovich was a close friend of mine. So I will let you speculate about those characters. Okay, one more question. So let's take one from down here. So this space station is similar to what are sometimes called O'Neill space station. They is inside a large cylindrical wall, very long and cylindrical. Under the leadership of the physicist Gerald O'Neill, NASA did a long, detailed study of designs for such a space station in the 1960s and 70s. No such space stations have been built, but if we spent enough money, we could build them. In the movie, the Earth is dying. Pardon?
Smoke, like in smoke. It's softer.
Okay. And to survive, people need to get off the Earth in an O'Neill space station. The problem is not to build such a space station. The problem is to lift the space station off the Earth. In the movie, this is done by turning off the Earth's gravity, or turning it down, which of course we have no idea how to do that. But in the movie, the people have seen gravitational anomalies where the strength of the Earth's gravitational pull is changing from one location to another in the way that nobody today has ever seen. Professor Brand believes that if he can understand these gravitational fluctuations, these anomalies, perhaps he can learn how to use them, control them, to turn off the Earth's gravity for long enough to lift these stations into space. I will now get technical for the physicist. If he could understand the action that is Lagrangian for the physics of the fifth dimension, then he would be able to see whether there are fields in the fifth dimension that are controlling the strength of gravity and learn how to manipulate them. And he realizes that if he can learn the quantum action, or the quantum effective action, from the inside of a black hole where it is manifest in a singularity, that from that quantum effective action he can deduce the physics of the fifth dimension and learn how to control gravity. And so that is why Cooper goes inside the black hole, to learn this quantum effective action, so he can tell his daughter how to control gravity, to turn it off so the space stations can be lifted into space. So all this is explained in my book, and I think, yes, this is conceivable if Cooper and TARS are smart enough to learn this quantum information inside the black hole, but they must be very smart. Let me stop there. Thank you very much.